Lightweight, portable, innovative. TESCO's 6330 meter site analyzer is the most versatile and complete tool for testing the entire functionality of transformer-rated metering installations. Contact us today for a free demo. All right, good morning, everybody. Can you guys hear me okay? All right, I'm getting a yes, so perfect. Thank you guys so much for joining us today. Are you there, John?
I'm here. It's all right.
All right, I can hear you loud and clear also.
My bad.
You're good. So thank you everyone for joining us on this Tuesday, February 23rd. It has been cold and snowy here in Bristol, Pennsylvania. Hopefully you are all staying safe and warm out there and are ready for another TESCO Tuesday session. So we're going to begin shortly here with meter testing in the field. We're trying something new this week. We've actually pre-recorded some videos to bring you simulated meter testing in the field. So you may see the video go dark a minute as we switch over to the videos. So don't worry if you see a blank screen for a few seconds there. We just want to give you guys a heads up on that. So it's not a technical glitch or anything. We've practiced this. Hopefully everything goes well, but we're going to be on the line for you guys. We're just going to take a few seconds. It might show a blip or something. That's us just switching from the presentation to the video. So we just wanted to make sure you all knew that. A few ground rules before we get started here. Please mute yourself so everyone can hear the presenter. Feel free to unmute if you have a question, but then mute yourself again afterwards so we can hear everybody a little bit better there. So you can also type your questions into the chat, which is on the bottom right of your screen. We'll also have a Q&A at the end of the session, so please don't be shy with your questions. There are no dumb questions. The only dumb question is the one you don't ask. So maybe someone else has a question and you could ask that for them, or maybe they're shy and don't want to ask it. So please ask away. We're here to help you guys. We're here to answer your questions. You can throw them in the chat. You can PM them to me. You can, whatever. We'll get your questions there. You can always reach out to us here at TESCO too in the office with any questions you have, or shoot us an email. We'll be glad to help you guys. And after each session, we will also post a copy of the presentation as well as a video of today's session on our website at tescometering.com/TESCO Tuesdays. And if you guys are signed up on our email blast, you will get that as well. It'll send you the little clip. You can just click on there and watch the video or download the presentation. So without further ado, it looks like it's just about 11 o'clock here, and I will throw it over to you, John, to begin meter testing in the field.
Thank you, Andy. Appreciate it. Welcome, everybody. My sound okay coming through, Andy?
Yeah, you sound great.
Perfect. Okay. Well, don't know about that, but that's okay. So, yeah, welcome again. And we are trying something a little different. And as Andy said, we're trying to step things up a little bit, change things up a little bit. If there's any particular topics that you have out there that we haven't covered or you'd like to cover, like Andy said, don't be shy. Tell us what it is that you want us to do, and we'll certainly do our very best. But today we're going to do, like I said, a slightly different take on this. But essentially what we're going to talk about today is a topic that's not particularly new, but there's some new techniques out there, new testing facilities are out there. And there's also the fact that these are sort of things that we can do a lot easier than we used to be able to do. So we call this meter testing in the field. However, typically when we do all these presentations, we're often at meter schools, we're often at trade schools, we're often out there meeting with you in the field physically and going out to do these tests. And unfortunately, circumstances being what it is, we're not able to do that. Yeah. So what we're going to do is we're going to bring the field to you. Change. We're going to have some little videos that we prepared where we got some testing in our laboratory back in Pennsylvania. Okay, so let's look at some of the topics we might cover. We're going to cover sort of test switches generally and CTs. We're talking today about testing in a transformer-rated customer site. These sites are particularly valuable in the sense that the utility really gets a tremendous amount of its revenue from these sites. And typically in most environments and most companies like yourselves or your utilities, you could have anywhere from 80 to 90% of your customer base might be residential, but then there could be 10 or 15% would be commercial or industrial. And the problem is that represents probably close to 45 to 50% of the revenue of the company. So there's a lot going on in these sites, and we think it's an important topic to cover multiple times because if we get it right, you can save a great deal of money and identify problems. And we'll talk a little bit about that later on when we do this. So we test switches and CTs. We're going to use in our laboratory, and we have Fran as well with us, who might be able to give us a little bit more background on this, but this is one of our MTS 3050 true three-phase testers. As you can see, there is a meter in there, a socket there with everything connected. We are going to use this because this gives us the ability to replicate a customer site. We can generate three-phase voltage. We can synchronize it with the 120-degree shift between them all. We can also do the voltage and the current. We can do current as well. So we can generate quite a substantial amount of current. So we can actually drive the current through the CTs, which is something that's unique that you'll be able to do in a factory environment rather than an actual site test. But it replicates it pretty well. You'll see for yourself when we run them. So we're going to do customer load initially, and we're going to talk a little bit about why we do customer load, and we're going to do a little test on that one. Then we're going to show you a little video of that, of actually doing that test. And then we're going to continue with the CT ratio, which is an important test. CTs themselves represent a key component of any kind of testing that you're doing. They are actually going to be passing all their information right onto the meter. So if there's anything wrong with that CT, you may not see it initially, but you'll find out when you look at the billing content. So it's an important test to do, relatively simple, but nonetheless, we'll show you how we do that, and we'll get a little video of that one. We also then going to do a phantom load test towards the end of the presentation to show you what happens when we do a separated phantom load, where we're shunting out the CTs and we're testing the meter out with a known source. And we'll have some time at the end for a Q&A session as well. So does anyone have any questions right now? It's pretty early on, but just thought I'd ask. Okay. Pass on to Andy. She can text me. I've got as well. So I have a full screen here, so I don't see everyone's participation side, so I can't see the texting. But we'll be good. We'll be able to answer them for you. Okay, let's talk a little bit about transformer rated metering. So essentially, the meter, it really is a scaled down representation of the load. And you can see the little pictorial we have there. The scaling really is accomplished by using the external CTs. And sometimes we also have PTs as well. Those two combined will give you your billing multiplier. And that's a valuable number to have, and it needs to be accurate. And often in time goes by, there's an assumption that they are correct. And it's not until you do a test on the site that you establish that perhaps they're not. So it's an important test to do. And as we point out, the meter is not, generally speaking, part of the circuit. It can be removed. And when you remove that, it doesn't shut any customer down. It just allows you to do a replacement meter. One of the decisions, certainly for this type of product that we are using today, is a field test unit to avoid removing the meter. It's possible to take a meter out and do a standard test in the field or in a laboratory to establish the meter's accuracy. And there's nothing wrong with that. That's fine. We do that as well. However, when you're in the field and you're at a customer site, particularly a three-phase customer, there's always an element of risk to a certain extent when you remove a meter and put it back in. So in order to avoid that, this is kind of a non-invasive test. So you'll see how we set this up. Quick overview. I think most people on this conference call are probably familiar with CTs, but it doesn't do any harm just to have a quick one-screen slide to show you how we set these up. So this is a typical 9S installation. These are 400 to 5s. So essentially 400 amps goes in, 5 amps comes out, goes into a test switch, which then goes into the meter itself. And everything's going to be ratioed. We'll talk a little later about nameplates, which are on all of these CTs. And it is not common, fortunately, but it does happen. You can even have nameplates that are incorrect. So you have to be a little cautious. And the advice I would say is whenever you're doing any test, a visual examination of what you have is probably more valuable than anything else. Do a visual examination before you do any testing. Look for obvious things. Perhaps even tighten up some of the torques on some of the nuts and the bolts and the various things that are in the cabinet using all the safety tools. I've seen that done too, and that can be a very interesting and a very good way of preventing any future problems. So meter accuracy testing, we're going to do a customer load test. So essentially what we're doing is we're using one of our 6330 units, which is going to be able to do the test. The 3050 product we mentioned, you'll see it in the video, is being used to induce the current and the voltage there. But under a customer load test, you actually got customer load billing conditions. The other test we're going to do later on will involve doing a phantom load, which, as you can see, replicates a slightly different situation, but it's a repeatable test. And then we can analyze the data. We can look at waveforms. We can look at vector screens, all the metrology information. And a typical installation might be on the right-hand side in one of our pre-wired boxes there, where you've got a meter can, the lid comes off, and behind that is your test switch, which allows you to do safe testing in these environments. So why do we do these tests in the field, and why are they so important? As you can see in some of these statements here, with a single transformer that may be wired backwards would actually give a very inaccurate error, which was going to give you a third of the actual bill. That's substantial. That's a lot. A broken wire, for example, can reduce also the customer's bill. And ratios inappropriately marked that we mentioned, for example, a 400:5 instead of an 800 is going to give you half the actual bill. And the inverse of that, of course, is going to double it, which is neither good for the customer nor for yourselves. So it's a valuable test in these customers themselves. And like I say, it's going to vary. They're not the volume that you have traditionally. The residential testing is perhaps, but there's less capability, that there's less risk perhaps in that. So CT testing is important, and we certainly recommend that it's done at least annually on your biggest customers, your largest customers out there. Some of the important factors that we're looking at is cross-phasing, loose connections, maybe CTs are being reversed accidentally, even wiring may be incorrect. You may have dual ratio CTs. There's a whole range of different situations that you can find. And again, I can't say enough about a visual test, or a visual inspection, perhaps is the right terminology. Just do a visual. Those cabinet doors may not have been opened where those CTs are for some time. So do the normal, safety procedures, open the cabinet, do a really good visual and see if anything's obvious before you run the test, and then you'll be able to confirm it. So when we're doing the meter accuracy, you obviously want to be able to detect the IR pulse. So this little IR pulse detector that we have here on the screen, this is something we designed primarily to allow you to do pulse detection. It also allows you to connect it anywhere you want on these, and including as well at the top. We'll do a little, next time we do these, we'll do a little picture of a new one we just developed for the Itron meter, which actually comes out the top. So the light pipe for the IR port does not come out the front of the meter, it comes out the top, but we can still actually capture that. And the reason we're doing that is that we want to ensure that we do have a pulse before we start testing. It's not essential. However, I would say that I've certainly done testing in the past where this has not been available. And the problem with that is you don't know when you connect that on there whether you actually have a pulse or not. You have to rely on the instrument to do it. Having this gives you an indication of the power that you have on there. You have it lit up, it's working. And then you have a little received pulse, which gives you confirmation that you're getting your pulse when it comes out. This is typically the screen that we use when we go through our testing. So one screen only. You don't have to go through menu after menu after menu. It's pretty self-explanatory for the most part. You decide on your form factor, you decide on your case of H value, you decide on your test amps. You can change the number of pulses per revolution, but honestly, one pulse should give you the accuracy required. And as you can see here, there are different types of selections we can do for customer load testing, phantom load, light load, power factor, which we'll talk a little bit about later on. You are also able to do different types of testing, up to and including timed registrations, demand testing, energy testing. And then these little columns here will just indicate what's available to you when you select a load. In this case, how many pulses do we want? Any weighting factor we might want to add. For most times it's just one. And then how many times you might want to repeat the test. We're going to do one, but you can do 2 or 3 if there's a decent load, and that gives you a kind of an average as well, which is also sometimes a useful thing to do. Okay, so at this point, what we're going to do is we're going to try our little technology out. So I am going to indicate here, we can see a screenshot, but as you can see, we're going to move that over, and Andy is now moving over to the video. So let's see what we can see.
So here's an introduction to our 6330 meter site analyzer test setup. We're using one of our next-gen test boards. to generate a site. So we're generating a primary current, and then through the secondaries, feeding the meter. So we have pretty much a simulated customer load situation here for a 3-phase 4-wire Y. We have a 9S mirror. We have our 6330 already hooked up. We have the potential cables. We have the current cable from secondary current and also for the load box generated load. And then you have your probes, your Rogowski coils, which are connected at the back, and you have your connection. So from there, with this setup, we can run all the various tests, look at the transformer burden test, meter accuracy test, drive customer load test, light change test list. Ready to go. And we're on the main menu. So from here, I'm going to select manual mode, meter test. This is already configured for this meter, 1.8 kH. I have selected the test load over here, or customer load, and it's ready to go. You can also configure it for multiple pulses or multiple iterations. And for this test, we're just going to do 1 pulse. So it's just as easy as pressing start. The test is in progress. As soon as it gets the first photo pulse, it will start accumulating watts. Which is right about now. There it goes. And it'll do 1 revolution, which would be, for this 1.8 kH, would be 1.8 watt hours, would be a perfect test. And there it is, was an error of 0.02%, so this meter is pretty accurate. And it passed. And just press continue, and here is your tests that you've done, and you can save these in the site test results page in the database.
Did that, everyone's there okay? Hope so, look pretty good. So that was Fran White, who's one of our senior test technicians back in the factory, performing a small load test. As you can see, it's a pretty straightforward test. I mean, it takes longer to set the cables up than it does to run the test. But that's the whole purpose, is to make it easy, quick, reliable, that you can get these tests in the field. You know, we all live in different climates in the country. I live in Arizona, and it gets pretty hot in the summer, and I've been out in it doing testing with customers locally, and believe me, it's not a race, but you want to get there, you want to get connected, you want to leave that site fairly quickly when it's so hot out there. So there's a lot of advantages to this type of test as well. Okay, so we'll move on to, well, any questions, anything in there, Andy, at this point?
I actually did just... No, we're good. Sorry, wrong one.
Okay, we can catch up again. We're on track, so we can certainly give ourselves time at the end.
We also have Fran on the line too, who's in those videos. So if you guys have any questions, Fran is on the line to help us out as well.
Yeah, absolutely. Thank you, Fran. Appreciate the testing you did there. Yeah, if there's any questions, either of us will be able to answer them for you.
Sure.
Let's move on to having done the customer load test, a CT ratio test. One test where you are required to get into the inside of a cabinet. As you can see here, you can see the test switch, you can see the cabinet. This particular setup is a type of cabinet that contains both the test switch and the CTs, as you can see there. The pass-through CTs, you can see the bus bars and you can see them connected. And left to right, we have A phase, B phase, and C phase. So you can clearly see now what we need to do in order to do this test, of course, is to connect a primary, and we need to be able to connect the primary current, which we're going to call primary, which is here or clearly on the red Rogowski coil that we can see here. Then we got the B phase, and then we have the C phase. These, as you can see, were double wrapped. It is a feature that we offer, which means if you have a low customer load condition, and that could be simply because of the type of customer out there, it's difficult sometimes to pick up the primary. If you have a single wrap, you know, you're looking at 1,000 amp CT, so you need to have, you know, 10 amps-ish, maybe a little bit less sometimes, to be able to trigger the Rogowski coil to pick up enough signal to be able to actually read the current. If you double wrap, and now, of course, you're doubling that amount. The instrument will take care of that when you tell it. And you are telling it it's double wrapped, it will take care of that and make sure that it takes that out so you don't get double the amount of current that you think you're getting. Having said that, we can see here we set them up, and this is a true three-phase test. So we're doing all three at the same time, A, B, C. So we're running them there. You can see the duckbills connected where we're doing the other test setup there as well. So this is our secondary, and this is our primary. Now we have both. We can confirm what we have in terms of our ratio. This is typical of the setup that we had before. And as you can see, the calculated ratio in this case is 80:1. So what we're looking at is any proportional value coming through these CTs will be measured at the test switch, which is what the meter is actually receiving. So on the customer load test conditions, you're looking for a billing condition, which is what we said right from the beginning. It is the most practical. It is the most real world condition that we see. So what we'll do now is, instead of me going just screens here, we are able to do a small CT ratio test for you. We make connections to the primaries, we make connections to the secondary, and then we can connect the IR pulse. Most of these are already connected. And Andy's going to queue it up for us. So we should be able to see the next slide and the next presentation slide.
So now we're going to do a CT ratio and burden test. And we'll do this from the main menu, access the manual test, CT test. You can select burden and ratio, or you can select ratio only. And for this demonstration, I'll do each one separately. So now we're going to do a ratio only test. I've already set up the CT over here, but if you don't know, it'll figure it out for you. So it'll ask you whether it's been wrapped once or twice and figure out the CT ratio itself if you don't have it. So we'll start, and now it's done the 3 tests, and they are past 2, and now we passed 3 because I've changed the limits to 1.5. But yes, so now you have your CT ratio, and it came out perfectly.
As you can see, fairly straightforward. Once you have them set up, you're already measuring these parameters and you're looking at them on the vector screen as well. For those who are looking at the screen there, you may have noticed we saw initially a fail or a fail indication. I think it's worth pointing out that when we say it's a fail indication, this is not a catastrophic fail. All this means is, with the parameters that were set up, that you decide to set up, are going to test out the ratio against a particular standard, an accuracy class, for example. And that's part of the testing procedures that we do. And it's worth pointing out that on the nameplate, which we'll talk a little bit about later on, there are accuracy classes on all CTs. The question is, under what condition are they tested? And that's the key thing in the field here, that in a customer load situation, you're not able to control the load delivery. It could be random, it could be intermittent, it could be high, it could be low. So what you're doing is doing that test. So sometimes also positioning of those Rogowski coils is an important factor. Rogowski coils don't work like a standard clamp. The clamp's shook, and so anything in the center is measured. They can measure around the periphery of those the probes as well. So positioning them is important, and sometimes moving them slightly will get a much better result. So just to make to that, because the fail does not mean the CT has failed. It means it's not met the requirement that you asked it to do. And we'll talk a little bit more about it because that's an important point. Okay, so with that in mind, we're going to move on to a customer CT ratio test. Same, however, this time with what we call burden. And the reason we do this is because of this nameplate. And if you look at every CT that you have in your inventory, you'll see nameplates on them. They're tested at the factory, they're delivered to you, and then they're installed. One of the components on that list that you see here is here. There's an example that we've highlighted where it says 0.3%. That's the specification of that CT accuracy based on at a burden of 0.1 ohm, 0.2 ohm, or 0.5 ohm. What it's basically saying is there should be less than 0.3% change in your secondary current that you're reading at your test switch from the initial reading that you did with zero burden, which is why we give you the choice to do a ratio only, which is what it does, which is at zero burden condition, or whatever burden's in the system. Or you can do a test with burden and you can select it. So in effect, what this represents is a stress test for your CT. You're trying to predict what would happen in the customer situation if you added more burden to the system, which is not catastrophic, but there's certain points at which it's going to stress it and the accuracy will degrade. So that's what this test is basically about. And this is just one example of how we set that one up. When you're doing the functionality test with burden, some burden will always be present. There's always got to be there. You've got resistive wires everywhere. You've got connections. You've got resistive contacts. These are all going to be things that's going to be something that you're going to actually see. So it's important to notice that. CTs also must be able to maintain an accurate ratio with the burden on the secondary. And that's, again, an important part of what this meter is seeing. Because visually, when you're on a panel, that's the only thing you generally see. So behind it is everything else, which is why we do this test. And here's an example of it, which we'll also show you a little bit later on as well. And we'll do a test run with the burdens. And you can see here, it's trying to replicate each of those burden positions. Another representation for you of the functionality with it is this little graphical representation with some values here. And you can see here, for example, if you had an initial reading of 5 amps, that's an example that we're going to use, you're looking at 0.3% of your 5 amps, which gives you 0.015 or 15 milliamps there. And then what you're looking at is the 5 amps at the secondary minus that error, which gives you 4.985. What that means is there's going to be a roll-off at some point where it's going to degrade, where you're not going to get the 5 amps at your secondary. It has to be fairly substantial to do it. In this example here, if you look at the 4 amp position, you're looking at 4 ohms. That's a significant amount of resistance that could be in the circuit. That could be due to a major issue that may be going on. The important thing to remember is that the customer wouldn't know and nobody would know because everything would still function. It's not a catastrophic failure. And that's why it's important to detect these early on. Because you could have a very large customer who could be a megawatt customer. You may have some condition that you're not aware of. And when you come to test it, it could be years later before you discover it. So this, again, is another interesting test that we do to try to replicate and see how those CTs perform under this stress condition, which is controlled. Just one screenshot of an idea of what they look like. Well, this was done before we done the video, so now we get to be able to look at that as well. But it shows you the ratios on the left-hand side here. So what we'll be looking at in the video is you need to pay attention. See here, you won't be able to see it as clear as this, but you've got the burden condition at 0, then the burden conditions at different values of ohms that we're going to put into the service. And you can see here, it's pretty good. I mean, we're getting a very short amount. We're not getting any more than a few 0.3% perhaps in this case. But each one of them is then run right through the system. So you get CT1, CT2, and CT3. So at this point, we'll do our third video now, and we'll try and show you how we're doing this with the burden condition as well. And if Andy can share the screen with us, we can do another video of this one.
So we can run these tests as burden plus ratio, ratio only, or burden only. And for this test, we're going to run the two together. This way you only have to press start once, and it'll test all 3 CTs at both burden and ratio test. And by extending the limits, you can change the pass-fail ratio, and you can also go and you can analyze all your results through these different ways of looking at them. There are many, many ways to analyze the data on your ratios and burden. And you can save your results. There you go, just so easy. So So we can run.
My apology. I think I jumped in just a little ahead at the end of the video, but it was finished, I believe. We could rerun it later if we want to see that again, but I think it was pretty much done. Fran ran the test. You saw the test result. It's pretty quick. It will run the A phase, the B phase, and C phase and give you the accuracy class. And what it's giving you is the parallelogram that we're familiar with, which identifies, if you like, a cluster of values based on all the parameters that we're testing. Ideally, you want them all to be within there, but it's not, again, catastrophic if they're not. It just means that you've gone outside the parameters under which you've tested. One of the important things to remember with the nameplates on the CTs is when the CT is tested, generally speaking in the field, or perhaps actually with the manufacturer, it's generally the specification is based on a number of parameters, rating factors, temperature, could be conditions, but it's also based on the actual current that's flowing through the actual CT. So one of the issues that we need to do is we need to check at what level the current is going through that CT. For example, if an accuracy class is determined at 0.3%, that assumes, in this case, a 400 to 5 CT would be 400 amps. Now, if you run 100 amps through that, that's significantly lower than the 400, which means you're not going to get the accuracy class. So I think we had a little question that came through. Is that right, Andy?
Yes.
Okay. Do you want, Fran, would you like to answer that, or do you want me to? Why would you not have the limits extend? Why would you extend the limits so it doesn't show a fail? It's confusing people.
Yeah, some of it can be rectified by moving the Rogowski coil, but also sometimes there's additional burden in the circuit. So I think as customers get used to using this, they begin to see what is normal for their burden tests, and depending on which CTs are in there. But yes, many times you're going to have to move the defined limits to possibly 1.5 times to get the CTs in. This is because partly the nature of a burden test is to add the burden that is listed there into the circuit, but there will be also whatever burden is contained in the circuit already. So it will actually be more than what the burden of the, if you add the burden rating, it'll actually be a little bit more than what the burden class is.
Yeah, no, I agree. To follow up on that, it's one of our colleagues mentioned this. I think part of what we see when we go out and do this testing is, remember, we're doing this testing under a customer load condition, which is variable. You may have a customer that has high induction motors which are not running on a line. You go to do a test and those motors kick in. Now you've got a significant load. So that's going to change the dynamic of your testing. So it's an ongoing test during a changing condition. When we do laboratory testing, that's not usually the case. We are got a very consistent level that we're looking at to get a repeatability of this. So it's important to know that in the field, you are going to get variations, and CTs are designed to do this. To give you an example, I recently did a test with a local customer here who has a units, and we did a test on a brand new rental return location. It's like a satellite for rental cars where they just drop the cars off. They sign them in, they leave, and then they're done. And the only really load that they have is a small office and a car wash. When we ran the test, they just put in 600 to 5 CTs. They are multi-range extended CTs. We actually measured the primary, and it was 8 amps on the primary, which means if we ran that test expecting to get 0.3% accuracy based on a 600 amp flow through that CT, we are not going to get it. It's going to say fail. So the limit extension ability means you can change it to see at what level that condition is passing under 8 amps. It's a valid test and it's a valid measurement, and we actually measured okay, even at that significantly low level. To give you an idea, typically up to 90% of your CT range is where most of the testing wants to be done. That's very difficult to achieve when you have a variable load. this particular customer perhaps is not likely to pull at least maybe more than 100 amps or so. So having 600 to 5s is perfectly okay, but you have to accept that it's 600 amp is here, 100 is there. So you're not using the full extent of the range of it. So when you do these tests, you can see, and the ability to be able to change those on the fly is really valuable, because you can see at what level you can make notes of what's going on. It does not change what we've recorded. It doesn't change any of the actual data that we recorded. That's not affected. All we're doing is we're giving you abilities to change the values to see at what point it would have passed. I hope that makes sense. It's kind of a long way of describing that, but in the field, when you run a unit like this, it becomes much clearer. You see the dynamics there, and especially if a customer's load is changing. Then you run the same test again the second time, and all of a sudden, all the passes come up. So the pass or fail is not really pass or fail the CT to take it out because it's failed. It hasn't. It's failing the test under those parameters. And I think that's the key takeaway. It's the parameters that you set. We can guide you on that. We go with whatever you think you may be the right way. But as Fran has pointed out, when you do this, you sometimes need to make some changes and see what levels they are and do repetitive tests. So I would run this test maybe 2 or 3 times at least. And hopefully the load and the customer has altered, and you'll see the difference in the results. So I hope it's okay.
John, one other thing I'd like to add is that we're running this from a test board to supply the load, which is a little bit sensitive to load changes. And also we're running it at a very low level current compared to what the rating of the CTs is. So it does skew the results a little bit in the negative direction. I think you would get more realistic results with real load and real load closer to the ratio, expectations.
Yeah, no, absolutely, Fran. Appreciate that. Yeah, you're right. I mean, practically speaking, doing this in a laboratory is not what this unit's designed to do, but we can test it, and that's what we're doing. So we're trying to emulate the field conditions. That's why these tests are important under customer load, because it's going to vary. You might want 3 different tests of that customer when it's minimal. For example, an irrigation customer out here would have lots of pumps, pumping irrigation all over his fields. In the summertime, may not be so much. There'll be hardly any load. So you get 2 very different results. They're both right. They're just different circumstances. Okay, let's move on to phantom load testing. This is now an option we've had for some time now with this type of product. And what we're doing now is we're now going to that situation, which is a good segue, where you have a customer that normally has a decent load in their system, and it's designed that way, and that's what the CTs will provide for them. However, it's extremely low, like the one I just mentioned, where you have 600 to 5 CTs and you have 8 amps going through the primer. It's extremely low. We managed to get the pulse to detect. It took over 3.5 minutes to do it. So it seems like a quick amount of time, but when you're standing looking at this, it seems an awfully long time, but that's because of the load. In that situation, you may decide, well, we need to get a measurement today. So what we'll do is we'll control the load. So this is what our phantom load test will do. You're determining all the parameters from your test switch. You're determining all the parameters, and we have these little connections here, which is not the picture's okay. You can see where the connections are to actually bypass the current flow, but we need to ensure the CTs are shunted out. Absolutely. And the instrument, if you don't do that, will tell you that. If for some reason you either forget or don't do the shunt out on the CTs at the test switch, it will know it sees current, and it will not allow you to drive current from the instrument. So these are the sort of test jacks that we'd normally have for something like this, and you're all probably familiar with these, I would think, and this is how we're running this test in here. Phantom load testing is using the same screen, the manual test, and as you saw from what we had before, the only difference now is we have the choice to select the phantom load condition. When we run the test, we'll end up with meter results for each of the components of the full load, the light load, and the power factor accuracy under load conditions that we are now controlling. And that segues nicely into our final video for you, which shows you a phantom load test, and we'll be able to show you physically at the test switch how we've connected all this up. So if Andy can take control, and we'll show you this one, and this one will involve selecting directly at the test switch itself with the easy clips, as we call them.
to start a 6330 load box test, we have to switch from customer load to load box test the load. The way to do that is test switches, red, yellow, and blue handle. We'll pull those down, and then we will add the 3 jumpers, which will jumper out the transformer and inject the current directly into the meter. So now we'll do the load box test with the 6330 generating the load. So I'll do it from the manual screen. That's manual, meter test. Now here you have the utility, the site is already set up, but here is to select the test loads. And I will deselect customer load, select full load, light load, and power factor. And over in this window, you can set up multiple pulses and multiple iterations if you want. For this test, I'm just going to do one of each. So then we have the meter set up, press the start button. The amplifiers are generated 2.5 amps. And then as soon as it sees a photo pulse, now it is accumulating watts. And for this particular meter, when you get to 1.8, there you go, it's finished. Now it's starting the light load test as it shows in the tag. So it'll run through. It's slewing to get quickly to a spot where you won't have to wait all day for the test to start. And certainly the test should be starting. It's now at 0.25 amps on each phase. And the test should start right now. There it is. So the light load test is a little bit longer. I know some utilities like to test at 5 amps and 0.5 because it cuts the test time down, but I think you're actually supposed to do it at 2.5 and 0.25. 1.7 and finish. Okay, so it finished the test. Now it is going into power factor, which is a 60-degree phase shift at each phase, so that it will be half power on the stator. And you can see the diagram here showing that the currents have shifted phase by 60 degrees. It started the test. And it's almost done. There it is. Now you can go to continue and you'll see the results. They're all passed and they're all under 0.1, less than 0.1% error. You can also change in the configuration screen, you can change this to registration if you'd rather look at the results at registration. And there we go, and that is the load box test.
Hey, John, as you change back there, I had a question come in when the video was rolling about when would you perform a customer load test and when would you perform a phantom load test?
Okay, yeah, it's a great question. I mean, this comes up a lot, actually, in most of the testing we do. There's a number of answers to that, but the quick answer is a customer load test arguably is the most real-world condition. You want to get the customer load, you want to get the conditions, and you want to get the billing conditions. However, it's not always possible. So the phantom load allows you to run a test on the meter. It doesn't test the CTs in this case, but it will certainly test the meter in the conditions using our load box, which is driving, in this case, the test amps that's required from the meter, which is typically 2.5 amps for full load. And as Fran pointed out, now you have a 10% test, which is light load. And then you repeat the same thing with a power factor of exactly 1 and a power factor of 0.5 with a 60-degree phase shift. The reason for that is you're not able to get a customer actual load to run. So we're controlling it by giving you the worst case and best case. And that is a very normal test. It's an ANSI test. The other thing that comes up sometimes is depending on the type of utility, if it's a public utility commission audit or if it's an investor-owned utility, they often are required to do the phantom load test because it replicates the same situation and scenario every single time. It doesn't test the CTs in this case, but for a meter test, it is significantly giving you the same reliable test with a traceable document or a traceable piece of equipment, which gives you that confidence that every time you publish the result, it's using the same circumstances. So it really sometimes is a question of what's the best for the service. You can do both. As you've seen from this, the time that it takes to do a customer load and phantom load is slightly different, but they really are fairly quick. I mean, you can do the whole thing in less than 15 minutes. So it's a pretty quick test. Okay, we've got about 15 minutes left or so. I wanted to touch a little bit on harmonics testing. It's something that we've talked about in the past. This type of topic almost deserves its own little conference, and I've done these many times in the past. But just a quick overview for us on this to give you an indication of why we do this and why it's important. Because these days, as we all know, most of our loads these days are nonlinear. It's just the way of the world. We're an inductive load. Harmonic conditions are really basically systems that are driven by the currents themselves, by the loads mainly. What you're looking for is to see the worst case on each of these. We're not going to do a harmonic seminar here, but to give you a value, the total harmonic distortion is what we all look at. And that takes into account a calculation which is based on all the values that you see. In this case, there's a voltage total harmonic distortion, and there'll be a current total harmonic distortion, and they're very different. The voltage harmonic distortion generally needs to be less than 5% of the value that you're testing. 120 volts, 240, 208, whatever it may be, 277. That's because everyone else is sharing the same circuit. And if there's any content, it's going to propagate through the service, which could affect someone else. So there are obligations to meet these requirements. There are IEEE 519 rules out there. There's regulations. So all of these tests are done essentially to assess, again, what you have. It's like an emissions test almost. How much do we have? It's acceptable to have a value here that's something that's going to be less than that, but it may affect other customers. So the question is, what's going to affect your customers? I've done many tests in the past where we've had a mixture of customers in a sort of an industrial area, one of which was very sensitive to any changes in any harmonic content. Another one was fine. And you get crazy situations where you might get a semiconductor manufacturing plant, which is very sensitive, and not far away in the same branch is an arc welding furnace that's firing away 3 or 4 times every few minutes. And that can cause a tremendous amount of harmonic content. So we look at this in different, these are some screenshots that I took recently on a test I did where we're looking at the voltage. Here is the red phase. You can see the red one here. You can see the yellow phase coming in and the blue phase. So you can see all the voltages there, which are not too bad at all. They're sinusoidal, they're fine. Slight edge on them, but nothing significant. The current, however, as you can see, is quite distorted. It's still sinusoidal. It's still performing what it should do, but it has got a lot of distortion in it. And the frequencies in a power grid can cause power quality problems. This is not detecting power quality. However, if you're on site doing all this testing, this is a great tool to have to at least get an assessment. When we did all our testing, we met all the requirements and we got a profile. So next time you go to that customer, if there's a change in their service, if there's some change of how they're performing the test, maybe a service has changed, maybe there's another building that's been added on or they've extended it, how has that been affected and what's going to happen? So with harmonics, the way to look at this is to consider it as a invisible quantity, if you like. We generally don't see this, as we don't with most electricity. It magically arrives in our house and comes out the wall sockets until it doesn't, and then we know how devastating that can be. Well, the number one problem with harmonics in this situation is heat. Because the way that they propagate down the cables, particularly the current, is like a skin effect. So it kind of spins around. So those frequencies, when you think of a conductor and you think of a cable that's been designed, it's typically been designed to handle 60 hertz frequency right down the middle. In a resistive component, there's no other harmonics in there, so that's fine. But when you have additional harmonics, which is, if we go back, we'll see on here, you'll see the different components here. So you got the second, third, fourth, fifth, sixth, and so on all the way through. I won't go through them all of them, but you can see there's clearly a significance here as opposed to around here.
Hey, John.
So what are they and what they are? Go ahead, I'm sorry.
We got a question coming in. Is it possible to take into account interharmonics?
Yeah, we can. You can see here what we're looking at is kind of the integer values. So the second, third, fourth, fifth, sixth. If you want to get into the interharmonic profiling, that's something that you have to sort of calculate a little bit. I don't believe we do interharmonics at this point. In other words, you're looking at 2.5, 2.75, 2.85, and then 3. And that's the significant part of this, that I understand that. And yes, it'd be nice to be able to see them, but now you're dealing with a harmonics analyzer. And the product was really designed just to give you an overview. My advice would be, if you do this type of test with this type of product, you've got a good reference point to start with. If there's any doubt, my advice would be then to establish a harmonics analyzer or a power quality analyzer that can monitor it over a long period of time and assess the interharmonic capability. They do that pretty well, but that's a long-term test. You need to be running for at least a week. So you get in the weekend period, you get in the business cycle of the customer, and you can establish what they are. They can have an effect, yes, certainly with switching conditions that we get with AC, DC motors, drives, inductors, variable speed drives, all of these things have harmonic content. So it's a good question, and that's a whole another seminar we could probably get into too, but I appreciate the question. It's something that we might look into too, but again, we're not going to get away from the fact that it's not designed as a harmonics analyzer, but because we're measuring what we are, we're able to detect it. But the reason I mention this is the heat component on this, and this is something that you need to be careful of. I have seen some fairly severe conditions in the past where a transformer system may have been put in many years ago and was never really designed to handle the types of loads, and it can get to an overheating situation, and I have witnessed that myself, and it does get super hot. So you got to be real careful of it. Okay, can we reduce or eliminate them? My honest answer is no. To eliminate them 100% is extremely costly. I don't know whether it's truly practical. It's around us all day. We see it every day. We witness it every day. It's managing it. I think the secret to this, or the answer to this practically, is managing it. If you can reduce the most significant harmonics with some kind of filtering, inline filtering, that will significantly reduce the overall impact on both the current side and then consequently the voltage side as well. You can now, of course, when you look at transformers, you can get K-factor rated transformers. They're usually designed with built-in filtering. They have different types of bypass filters, and they put them in specifically knowing that the customer's load that's going to be attached to all this will have a significant amount of content. And that's a way to try to reduce it to a manageable level. And as you can see, these are some of the things we have, particularly that we know today, even in your own house. The switch mode power supplies are absolutely everywhere we go. So this is not something that's going to go away, but it can be managed. There's no doubt it can be. And there's some significant products that have been developed over the years that allow you to do inline filtering and a lot of different ways to reduce this to a manageable level. And these are some of the things that we talk about on these ones. And most of the times, power factor correction capacitors is actually a form of content too. When you think about it, that's the other issue we have when you have those that can actually reduce some of the content, because it's an inductive world. So what we're trying to do is add more capacitance to it to balance out the power factor a little bit. And that is something that does happen with large customers. I live fairly close to an Intel plant, which I've worked on many times in the past. I mean, they are just so incredibly sensitive with their operation, which is 24/7 every single day. And throughout the entire year, it never shuts down. So they're perhaps one of the most sensitive around, but not everybody is that sort of condition. So we're near the end of our presentation here. I'll just go through this really final slide or two here just to show you why we do this and the sort of reason why periodic site inspections are so important. You have to decide, obviously, when to do them. You don't have to do them every month or every 6 months, but certainly once every few years. And I would certainly recommend any new installation or any updated service installation is a good opportunity to establish what's happening. As long as you keep a record of that, and this instrument will allow you to do that, you now have the document to go and refer to the next year. And if things are degrading or perhaps getting worse, that's a time to then ask questions as to whether we do something. I mean, it could be a whole variety of things that we've covered today. But these are some of the typical things that we have. With billing errors may be detected. You may have diversions of currents, identify any potential safety issues. These are all part of the site inspection. And part of the site inspection is gathering the data, accurate data for yourself, so you can make, judged decisions on this about which direction you're going to go. Okay, we've got a few minutes, about 7 minutes or so, I think, nearly 5 minutes or so. Is there any? I hope you enjoyed the presentation on this. I'll be here certainly hanging around in the lobby, the virtual lobby, I guess, after this. But I do want to put a shout out to Fran White and to Andy and to Stephanie, who put all this together. It's the first time we've tried this with the videos there. I hope it worked out for everybody. Maybe we might get adventurous and try a live one next time. I don't know whether we're going to do that yet, but that would be interesting. But please pass us your information. Tell us what you like. Tell us what you want to do. And anything that we can cover for you, we'd like to do. So at that point, I'll hand it back to Andy and any questions we might have.
Thank you so much, John. Yes, that was the first time we tried that. We hope you guys enjoy it. And yeah, maybe sometime we'll try it live. So we wanted to make sure we could get that to you. It seemed like someone did have maybe a connection issue where the video was lagging, but they could hear the audio. So it seems to us that everything did record straight through. So that will be on the rewind video you guys can see. A little bit later today or early tomorrow, we'll get that up on the website for you, depending how fast it can download. I did get a couple questions coming in here. The first one, do you need to have a 120-volt auxiliary power source when doing a field test?
Yeah, it's a good question. Yeah, obviously in the lab we have here, we can connect it to any source we want, 120-volt outlet. However, typically they are not, on the side of a building, or they're in the middle of a field somewhere, or they're on a pole. So it's not so easy. So the design of this product was designed specifically to have a replaceable lithium battery. The battery is a pretty good technology that we put in these, and they are lasting a long time. Even the customers that we're seeing now, we're getting them to feed back to us how long it's taken them before they recharge, and they're getting through a few days before they need to consider that. That's a remarkable improvement over the years ago. So the answer is no, you don't need 120 volts. You don't need to connect to the test service, which is certainly a possibility in other products years ago. That's okay, but you've now got yourself connected to the same service you're testing. You just got to be a little careful. I think having a battery gives you the ultimate isolation, and you're getting all the accuracy tests that you need. Anything happens, you've got a little recharging tray that we provide, put a new battery in, slot it in, and you're good to go. Well, that's a great question.
Thanks, John. Next, well, I just want to say too, you guys can go ahead and throw your questions in the chat as well. If you have a question, feel free to unmute yourself as well if that's easier. And we will try to get those to you. And don't forget, next week we'll have transformer rated testing using pickups and probes. That'll be next Tuesday. And then we have a two-parter coming up the next 2 weeks in March, the traditional ratio burden admittance and DMAG testing. It's a two-parter, and be sure not to miss that. If you guys are not signed up, you can go ahead to our website and sign up for that. And we'll also have the email where you can sign up as well, going out to anybody on this call today. So one other question I got here so far, I apologize if there's background noise. It's a little noisy today in the office. Do the Rogalski coils require batteries?
That's a good question too. Yes, in the past they have. And you can purchase those to work with other products, like a handheld meter of some kind, just to measure current. And they generally do have a little adapter which has a battery in it, typically a 9-volt battery typically is in there to power it, which is fine. However, unfortunately, if that battery somehow is failed, something's wrong with the switch that may be on there because you're putting that away and the switch gets knocked, you've now got no way of measuring the primary. So to avoid that, we provide all the power, the DC power, to those Rogalskis from the instrument. So the battery is provided by the product, which is then providing power to the Rogalskis. So when you go out, you absolutely will get measurements every single time. It's a great question. Yes, they used to have them. We decided against that because there's a possible risk of not having any primary measurement if you lose a battery. Any other ones, Andy? Uh-oh, we lost our audio.
Can you hear me now?
We can now.
Okay, I guess I was typing so people could hear me when I was in the chat there. Chat is kind of quiet. You guys are either shy or quiet, or maybe we shocked them with our videos. I don't know.
I guess we did. Yes.
So we're always here for you guys. If you have any questions, you think of something afterward, you're watching that video and you want to shoot a question to us, we're always here. And we'll hang out a bit and see if there are any more questions. And otherwise, we hope to see you guys next week. And actually, let's see. So I don't know, John, do you have anything else? Fran, do you have anything else to add?
No, I'm good. I'll be signing off. Thanks, everybody. Happy to participate.
Thank you, Fran. Appreciate it.
Thanks, Brian. Appreciate you. Thank you so much for that.
You're welcome, John.
Okay, so it looks like we have one question coming in. During the test on the video, it showed power factor results. Are those vector or, I don't even know how to say this, arithmetic power factor results?
Arithmetic.
Sure, that sounds better.
Arithmetic. That would be far away. Yeah, if I can recall which video it was, but when you're looking at the phantom load test, for example, we generate the full load, which is 2.5 amps or 5, as Fran mentioned, and we generate the conditions that we need to do to run the test. Part of that is to test for power factor. In this case, as we mentioned, this is a purely resistive load situation, unlike a customer load. So we are generating that ourselves, and the vector screens are therefore going to give you the actual voltage, the actual current, and the phase angle between each one. That's giving you the actual phase angle between voltage and current on each phase, which is giving you your power factor. So the vector screen is your friend. That's going to give you the live screenshot of that, and that's why we keep that up when we run the test. That's an important way to do it. But it's a good question, yes. And you can obviously take the data from all of the tests. You can calculate a lot of these things out. But what we're trying to do is, and as we do in the instrument, the 3050 that we use to generate this, we will generate a 60-degree phase shift, which will then create a 0.5 power factor. So we're doing the cosine of it. We're getting into some of the high theory stuff now. But it's a good question. Thank you.
Excellent, thank you. I don't see any others. I know you guys are all kind of maybe pressed for time. It is just about noon here, or just turned noon, so we can let you guys go. We'll still hang out a bit. If you have any other questions, we'll hang on a few more minutes. But otherwise, thank you guys so much. We really appreciate your time. We appreciate you coming back every week, doing these with us. And if you have any suggestions, anything you want to see, feel free, let us know. Thank you guys so much.
Thank you. Have a good day.